I'm changing my share so that you can hopefully see what I'm writing. And just to make sure, we're talking about this problem right here. Is that correct?
Yeah.
Okay, so this one is about energy and changes of state. And let me move my paper around a little bit. It's zoomed in a little too much. I don't know what's happening up there, but it's raining here.
Yeah.
Okay, that's a little better. Okay, so the question states, calculate the energy change to convert 500 grams of ice at negative 50.0 degrees Celsius to steam at 200.0 degrees Celsius. And they give us that the heat of fusion is equal to 333 joules per gram. And the heat of vaporization is equal to 2256 joules per gram. And the specific heat capacities of ice, water are given in the index, Appendix D. We know that the specific heat capacity of water, so I'm going to use W for that, is 1 calorie per gram, and I'm going to put degrees Celsius. And if we multiply by 4.184 joules per calorie, we know that it's 4.184 joules per gram per degree Celsius. So that's water. For ice, and I'm going to use the letter I for ice, okay? So they tell us Appendix D, so I'm going to move to Appendix D. And luckily, they're in alphabetical order, and Appendix C is at the beginning of the alphabet because I screw up once you start getting to L. I don't know what's after, I don't know what's. H is probably as far as I can go. And then I have to start saying the alphabet to know what comes after what. Do you know what I'm talking about?
Yeah. I have the value written down.
Oh, you do? Well, why are you making me do this then?
It's 2.06 joules per gram per degree Celsius.
3.06 joules per gram per degree Celsius. And what about the specific heat capacity of steam?
Oh, it's 2.06, not 3.
Okay, I can correct that.
Sorry, and steam is 1.86.
1.86 joules per gram degree Celsius.
Yes.
Okay, I'm going to draw a very small little diagram here that goes from negative 50 degrees Celsius to 200 degrees Celsius. And 100 degrees Celsius is about right here. And 0 degrees Celsius is about right here. So each of these is about 50. Not really to scale or anything like that, just so that we can see what's going on, okay? Now, when we go from negative 50 to 0, that's ice. You have ice all the way up to 0 degrees Celsius. And do you see this number here, the 2.06?
Yeah.
That tells you how steep the curve is. So when you look at these curves, you've got one that's 2.06, one that's 1.86, and one that's 4.184, right?
Mm-hmm.
The 4.184 is the steepest, and that's for water. So I'm going to make this curve for ice look like this. And that's the ice swarming. And I'm going to call that A. And
Okay.
on the bottom, we have the energy needed. And we don't know how much that is. That's what we need to calculate, okay?
Okay.
Now, do you see this heat of fusion and heat of vaporization?
I have a question about that.
Yeah.
Are those numbers specific to water?
Yes, they are. And you don't want to memorize, I don't have anyone ever memorize heats of vaporization or heats of fusion. But you should memorize the specific heat capacity of water because it's defined.
Okay. So just water, not ice or steam?
No, I don't even know those. Okay, so do you see these numbers here?
Mm-hmm.
The larger the number, the more energy it's going to take to make that happen. So you can see that fusion, which is melting, is a smaller number than vaporization. So I'm going to make this look like that, okay?
Mm-hmm.
And I'm going to call this part B. And then once all of the, so what's happening here during A is the ice is warming. What's happening during B, where there's no temperature change, the ice is melting and the ice and water are in what's called thermal equilibrium. So they're both the same temp. So you can't have a change in temp there. That dot I've drawn at the end here is when all of the ice has melted and now we just have pure water. When you add any more energy to it, the water is going to heat. Now, remember how I said that line there tells you how steep the curve is?
Yeah.
So here we have a curve this steep. This one's going to be steeper.
Right.
And it's going to go to 100 because what's happening is the water is warming till it gets to 100 degrees Celsius. I'm going to call this C. When it gets 100 degrees Celsius, it starts boiling and it starts turning into a gas. So now you have the steam and the water at the same temp, 100 degrees Celsius.
Mm-hmm.
So why am I making this line so much longer than the one below? Because this number is so much bigger than that one.
Yeah.
In fact, I should make it really, really long, but I didn't try to make it to scale, okay?
Yeah.
I'm going to call this D. So when D is flat here, you have steam and water both at 100 degrees Celsius. Now, what happens to the temperature of the steam once it's all steam and no more water? All the energy goes into increasing the temperature of the steam. So I'm going to call that E. All right. So here we have all the information we need. Here we have an idea of what's going on. And now I'm going to tell you that for this graph, you have two different types of calculations.
Mm-hmm.
You've got the flat, where there's no change in temp. Another way to say that is the change in temp is equal to 0. For the calculation, the Q is going to be the heat times the mass. And so when I say heat, I'm talking about heat of fusion or heat of vaporization.
Okay.
Now, when you have the, so this part here where it's not flat, we're going to call that a rise. Is that okay?
Sure. Or incline?
Incline, rise. Rise has fewer letters.
Okay.
So here we have a yes change in temp, which to say that change in temp is not equal to 0, right?
And that's the specific heat.
Yeah, and here you're going to use Q is equal to Cm delta T. And another way to memorize this is C is equal to MCAT.
Yep.
So which sections are we going to use the flat method for calculating the heat?
So B and D.
That's right, B and D. And which sections are we going to use the rise method?
The rest.
So A, C, and E.
Mm-hmm.
So rather than do this whole problem out, I'm going to give you one example of a B, or of a flat, and one example of a rise. Okay? So I'm going to go ahead and do A and B. So for section A, which is a rise, the Q for section A is equal to the specific heat capacity for section A the mass for section A, and the change in temp for section A. And the reason I'm putting all these letters here is so that I make sure I know I need the values for section A. Fair enough?
Yeah.
So what is C for section A? Well, C for section A is the specific heat capacity for ice. So I have 2.06 joules per gram per degree Celsius. The mass is 500 point grams. And the change in temperature is always the final minus the initial. What's the final temp here?
0 degrees.
0. And what's the initial?
-50.
Right. So this is a little weird. It's 0 degrees Celsius minus -50 degrees Celsius.
So it's positive 50 degrees.
So it ends up being a positive, correct?
Yeah.
So when we do the math in our heads, which is what I'm going to do in a moment here, can you see that 0 minus -50 is plus 50?
Mhm.
And 50 times 2 is roughly 100. And 100 times 500 is going to be roughly 50,000.
Mhm.
How many significant figures are we allowed?
3.
Yes. We have 3 zig figs here, 3 zig figs here, but also here, when you do this difference, this 0 is exact. We define the melting point of ice as 0 degrees Celsius. So this has an infinite number of zig figs. This only has 3. This is good to the 10th. This is good to the billionth, or whatever you want to call it, right? The infinitieth. So when you do the difference here, it's good to the 10th, which means positive 50, 3 zig figs. Okay?
Okay.
So I'm going to do times 500 and times 50. And I get 51500 joules. And if I write it this way, this does have 3 significant figures because trailing zeros don't count. Okay, so that's an A. B, I'm going to raise the paper up a little bit here so you can see B. B is actually easier. I'm going to do Q for B is equal to H for B and the mass for B. Now with this problem, the masses are the same everywhere, correct?
Yeah.
We're taking the same mass of water. So what is B? B is melting. So I want to use fusion. So I get 333 joules per gram times 500 grams. Now notice there's no temperature change in this problem. There's no temperature in this problem because the temperature change is 0. If we tried to incorporate that, we'd get 0 here.
Right.
Okay. So what is 333 times 500? The way I actually estimate this is I do something like this. I say that 500 can be thought of as like half, right? It's not half, it's 500, but if it were 0.5, it'd be half, right?
Mhm.
So what's half of 333? About 160, 170, or 165?
Mhm.
So I think the answer's got to have a 165 in it somewhere, followed by some zeros. How many zeros if we had to guess? Well, I'd guess 1, 2, 3, 4, 5 zeros. And actually, I shouldn't say 5 zeros. It'd be 165 and 3 more zeros. So I think it's got to be like 16,500, roughly, right?
Yeah.
333 times 500. So if I don't come out with like a 165 at the beginning and I get like a 362, I'm a little disappointed in my calculator and myself for using it wrong. And I'm happy. I get 166500. Now, where is this good to?
Hmm.
How
Well,
many
they're all
zig figs in 333?
3,
3. How many in 500?
3,
3. So how many do we get here?
3.
So this is good to the, if this is the 1, 10, 100 spot, it's good to the 1,000 spot, right?
Yeah.
What about this one here? What is this one good to?
Which one? A?
It's good to the 100 spot, right?
Yeah, 3.
So when we add these two numbers together, where would we round to?
The 100?
Nope. You round to the place that is less precise.
Okay.
Aren't hundreds more precise than thousands?
Yeah.
Okay. So the bigger the denomination, so to speak, the less precise it is. These aren't denominations, of course, because money is exact. You can't have a penny.
For B, the significant figures, since that's a defined amount, is that not unlimited significant figures?
Which one?
The specific heat of ice or the heat of fusion?
Oh no, those aren't defined, those are measured.
Oh, okay.
The only specific heat capacity that I know of that is defined is the one for water.
Okay.
All of the others are measured relative to water. And that also includes heats, heat of fusions, heat of vaporizations, are all relative to that definition of 1 calorie based on water.
Okay.
So it's that's the only one. Okay, so can you see that we're going to have to do 5 calculations and add them together?
Yeah.
Okay, so that's why I only want to do A and B, because the rest are the same, only different.
Okay.
Okay, let's pause this now and let's take a look at your quiz. Is that all right?
Yeah, let me find my work. I saved the.
And I'm going to share with you my, hopefully my, what do you call this? My browser. So I'm going to scroll up so that you can see that this is module 4. And if we scroll down, we see lab spectrophotometry. So I'm going to open that up. And you can see here that basically you have to watch the demo video and get the data from the video. You have to write up your lab in your lab notebook and then submit images of your lab notebook. And when I say submit images of your lab notebook, I mean this lab, not your whole lab notebook, of course. That's kind of, I hope implied. So here's a whole lot of background that you kind of want to read through, but basically what we're doing here is we are measuring light as it goes through solutions. And if you can imagine, if the solution is colored, the more colored it is, or the deeper the color, the more light is absorbed. And I will tell you this, an interesting thing about solutions is that the color you see is the color not being absorbed. So if you see a blue solution, blue light is not being absorbed. Now, when we talk about blue light and visible wavelengths of light, you can see in this little graph here, the visible wavelengths of light go from about 700 nanometers to 400 nanometers.
I don't see a graph.
Oh, how about maybe I'm not doing the right share.
I just see the
Oh,
module.
I'm not sharing. I paused my share. I'm sorry. Do you see it now? Okay. Was that a yes?
Yes.
Okay. So do you see that we go from red to orange to yellow, green, blue, and what we call violet?
Mm-hmm.
So this is Roy G. Biv. If you look at it backwards and start at the blue, it's or violet, it's Vib Gyor. All right. So this solution, if you take a look at the absorbance means it's absorbing a lot of that wavelength. If it's high, if it's low, it's not absorbing that wavelength. So this solution here with that graph would look kind of orangish yellow because those are the wavelengths that are coming through, whereas the green and blue and violet are kind of being absorbed. Are you with me there?
Yeah.
So again, the low part of the absorbance spectrum is what's getting through. The high part is not. It turns out that the absorbance depends on how concentrated the solution is. Now, the reason for that is water doesn't really absorb light, does it?
Guess not.
Well, can you see through a glass of water?
Yeah.
That's because it's not absorbing light.
Yeah.
Can you see through a glass of coffee if it's espresso?
No.
It's absorbing light. That's why you can't see anything. Okay? Well, imagine that you make some Kool-Aid, red Kool-Aid, like this might be a spectrum of. Is it absorbing light?
Yeah.
Well, white light is made out of VIBGYOR. And if no light is being absorbed, you see white light. Our eyes aren't good at distinguishing blue from red if it's all coming together. So if you make Kool-Aid that's red and you shine light through it, that means that you're going to get a spectrum like this right here. Fair enough?
Okay.
Now, what would happen to that spectrum if you diluted the Kool-Aid, made it less concentrated?
The peak wouldn't be as high?
Correct. That's it. And the bottom, the place where it's kind of near the baseline, that would also change, but not as dramatically. Basically, if you halved the solution concentration, the whole thing would go down by half. But if you look at the 700 area, do you see what half is there? Compared to the, we'll call it the 500 or the 450 area. So where the big peak is, that's around 480.
Yeah.
If you half that, do you see how the peak's going to drop quite a bit?
Yeah.
But at 700, it only drops a little bit because there's only a little absorbance. Fair enough?
Okay.
So if we wanted to see a concentration difference, we would want to study this at 480 nanometers, not 700, because you can't see a big difference at 700, but you can see a difference at 480. Fair enough?
Yeah.
So that's how you figure out what wavelength you want to work at. You want to work at a peak. Okay, so here's some more stuff here. And this shows you light being shined through a cuvette. And you see how the light is green?
Mm-hmm.
So if we go back up to our spectrum up here, can you imagine that the peak is probably going to be high in the blue area, high in the yellow area, and the red area, but low in the green area. Fair enough?
Yeah.
Okay. All right. So we're going to be working with a solution called bromothymol blue. What's really interesting thing about this is it's a pH indicator, and it changes color with the pH.
We're not using cabbage water?
No,
Okay.
because I did this demonstration and recorded it.
Oh.
And you guys don't have a spectrophotometer at home. They cost quite a bit. So do you see the structure changes a little bit each time?
Yeah.
Like on the left, you've got that sulfur bonded to 3 oxygens and all sorts of things going on there. And you see in the upper right, there's an OH.
Mm-hmm.
When we go to the middle structure, the upper right no longer is an OH, is it?
Right.
And the sulfur is only bonded to one part of the molecule, not to another part of the molecule, right?
Yeah.
And then when we go to the structure to the right, the OH at the left is missing its hydrogen,
Mm-hmm.
and those little differences mean that the molecule will absorb light differently. So
What
the
is
reason the
PK?
molecule on the, pardon me?
What is PK?
pK is the pH at which you have a 50-50 of each of them. So if you have a pK 1 of 1.7, that means at a pH of 1.7, half of your molecules will be the red ones and half will be the yellow. If you had a pH of 8.9, half would be the yellow and half would be the blue.
So those are decimal places, not commas.
Pardon me?
The 1.7, that's a decimal in between, not a comma.
Correct.
Okay. I
Where you need some glasses.
told you I did.
Actually, they're commas, but they're supposed to be decimals.
Okay.
I need glasses,
Oh, man.
but I have them. Okay, so those are supposed to be decimals, but this person, Yikrazul, probably doesn't know the difference between a decimal and a comma. Okay, so we're not going to work at a pH below 1.7 because that's pretty dangerous. So we work at this range here around pH 9 in this lab. So what we do is we work with these two solutions. You can see one is in 0.001 molar HCl. That makes the pH about 3. And then we do one where it's 0.001 molar NaOH. That makes the pH around 11. So we're working at pH 3 and 11, which isn't too bad because the concentrations are so small. For instance, your stomach acid is not 0.001, it's 1 HCl. So it's a big difference in concentration, okay?
Okay.
All right. And I see I'm going to have to edit this a little bit because we should have molarity there. I'm going to edit it while we're talking. So edit. This assignment does not count towards the grade. Oh, I got to change that. Boom.
Are you going to grade our labs?
Eventually. I'm going to start on them today. I wanted to get your exams done because they have a bigger impact on your grade overall.
Yeah.
Each lab only counts like 1% of your whole grade. If that, or actually probably 0.5%.
I think they're weighted 20%.
Pardon me?
I think you have them weighted 20%.
20%, so 20 labs, that's about 1% of your grade for each lab.
Yeah.
Whereas your exams are more like 10%. Okay, that's better, and I'm going to save this before I make a mistake. Do not count, change that. File upload. And this is due the same day your exam. So make sure you get it done before your exam, right?
Mm-hmm.
Okay, so there's more background here that you want to read through. I give you a safety section, and then I tell you the materials, and I give you the procedure for face-to-face, and then I give you the procedure for online. And then let's take a look at the beginning of the video. I got to get rid of this rubric because the rubric is for 10 points. And let's take a look at the video. And we're not going to watch the whole video. We're just going to see the beginning of it. And the reason I want to show you the video is because there's two parts to it, okay? Module 4. Spectrophotometry videos. I should rename that lab demo. So here's part 1. And to get to part 2, do you see this little spectrophotometry thing at the top?
Yeah.
That's an actual link. And if you go there, this is part 1. And if we look at the left, do you see how there's a part 1 here and then a part 2 here?
Yeah. So
the part 1 is me kind of explaining the background, and the part 2 is me actually doing the experiment with the spectrometer or spectrophotometer, depending on how much information you want to give. 18 or 14. So do you see this spectrum here?
Yeah.
And do you see the colors at the bottom?
Yeah.
Notice this is backwards compared to what we were looking at before. We have violet on the left and red on the right.
Mm-hmm.
Okay, so you're going to watch the video and collect the data.
What data?
Concentration, absorbance.
Okay.
So you see right here where it says wavelength and absorbance. At first, you're going to collect that data, and eventually you're going to collect concentration and absorbance data.
Okay.
So the video, I kind of walk you through it, all of it, and tell you what data you want to write down. And then you got to graph things, and I tell you what to put on the x-axis and what to put on the y-axis.
Handwritten graph or on a calculator or what?
I usually like you to do handwritten graphs, like on a piece of graph paper.
Okay.
And if you don't have any graph paper and you don't want to buy any, you can always go online. And if you write in free graph paper PDF, you can find all sorts of PDF files with graph paper on it where you can just print a page if you need it.
Okay.
Okay, so that's the lab you'll be working on for today. And since we're here, let's go ahead and look at the next lab. I really hate watching my videos because my videos are nothing like I am in class.
Really?
Yeah. They're so dry. They're like, ugh. All right. I'm much more lively in class. Okay, so here I'm going to go to the next lab, which you only have one in module 5.
And both are due the 22nd?
Yep. Because they're both related to the exam you're going to take on the 22nd.
Okay.
So that's why I also wanted to get this lab out to you guys today so you could start working on it. This one is really straightforward in my opinion. So there's not much written about it. It's specific heat capacity. So if you take a look, it says write up all sections, your lab book, notebook, take photos. And then we talk about coffee cup calorimetry. So here I tell you, you want to read about this coffee cup calorimetry in the book, and then you want to try it. And for the procedure, I tell you, hey, weigh your pennies, weigh some room temp water, place it in a coffee cup. Any insulated container should be fine, but coffee cups work really good, styrofoam cups. You should have a thermometer in your kit.
Yeah.
And that should work. And you want to heat the pennies in boiling water for about 5 minutes. put them in the water, and then measure the temperature of the water after like 30 seconds with some swirling. And what you're going to do is you're going to find out how much the water temperature heats up, so you can calculate the heat it gained. That's how much heat the pennies lost, and then you can calculate the specific heat capacity of the pennies.
Oh, okay.
And you should be able to do the same for the dimes. And do you remember how you asked me, does the heat of fusion, is it different for things other than water?
Yeah.
Well, the specific heat capacity is also one of those things that's specific for the substance. So the specific heat capacity of zinc is different than the specific heat capacity of copper.
Right.
So those are things you can look up, and you basically want to try to adjust this experiment to see if you get pretty close to the real value.
Okay.
Okay.
So what would Tony want?
So data, what would Tony want? Left to your discretion. But when I say left to your discretion, it's going to be graded on what would Tony want? You with me?
Yeah.
So you need to think about, what would Tony want to write down for data? Would Tony want you to write down the mass of water? Probably. Would Tony want you to write down the mass of the pennies? Probably.
Okay.
Would Tony want you to write down the initial temperature? Probably. You with me there?
Yeah.
Okay. And so we're getting at that point of the semester where I shouldn't have to tell you exactly what to write down, but you want to think about it. And so here I'm throwing you to the wolves.
Okay.
Science. So this one is actually kind of fun because you get to work with hot water. But remember, you're not supposed to allow anyone to work with you because we don't want anyone to get injured. And I do put this little section in here for safety. It says, if you burn yourself, seek immediate medical attention.
How many pennies and dimes should we be using?
I'd use all 50.
All right. Do they have to be minted after a certain date?
Pardon me?
Do they need to be minted after a certain date?
Yep, just like before, because if the pennies are minted too early, they're made out of copper.
Right. So 1983 or something like that?
Yep. Basically, any that were minted when you were alive would be fine.
Okay.
For me, that's not the case.
Yep.
It's about half for me. Okay, so that's it. We're at 11:15, and I'm going to end this session. Let me do my change share. Oh, stop share. So now you see me, right?
Yeah.
Okay. Unfortunately.
Okay. I might
All right,
see you at
Charlie.
1:15. I'm not sure.
All right, that's fine. And if you're the only one that shows up at 1:15 and you want to just do problems from the book, we can do problems from the book.
Okay.
And I'm going to post something from yesterday where we did problems from the book. I don't remember which problem it is, but one of those problems was find the specific heat capacity of molybdenum if you stick it in water.
Okay.
Which sounds a lot like find the specific heat capacity of pennies if you stick it in water, right?
Oh, gotcha.
So there's a worked out example of how to do it.
From last night or yesterday?
From yesterday. I don't remember which problem it is. It's the molybdenum problem. If you look in the back of the book, it's one of the early, like, first 18 problems where it says you stick a molybdenum. I want to say it's like 227 grams of molybdenum in like 242 grams of water or something like that.
Okay.
And they ask you what happens. And they don't really say what happens. They say, what's the specific heat capacity of molybdenum?
Right.
And we're actually doing that with pennies and dimes.
Okay.
And I will tell you that, you know, the more pennies you have, the bigger temperature change you're going to see. So that's part of the working it out in the lab is if you use way too much water, you'll get a temperature of like less than 1 degree Celsius and you won't be able to tell what's going on. So that's something you want to think about, is how much water do I want to use compared to the number of dimes I use.
Right.
And if you can imagine, stick a bunch of hot dimes in a big old cup of water. What's the temperature of the water going to do?
It's going to take longer to warm up the more water.
It won't take longer.
Wow.
It'll only warm up half a degree.
Mm.
How well can you measure half a degree with a thermometer?
Probably not very well.
Not very well. But if you put a bunch of hot dimes in like, this much water in a coffee cup,
Yeah.
won't that water temperature change a lot more?
Yeah.
And it'll be easier to see the temperature change. You with me?
Yeah.
So usually you want to use enough water to cover the pennies or dimes, but not much more.
Okay.
So this is why you tune in, so you can get little hints like this.
Mhm.
All right. Thanks for calling in, Charlotte.
Thank you.
And if we see you later, great. If not, I'm sure we'll see you again later this week. All right. Toodles.